In this video, we will explain the concept of acidity and how to determine which compound is more acidic when comparing the two similar compounds. There are four factors that determine the acid strength. Those are element effect, inductive, resonance, and finally hybridization effects. No matter what the factor is, same procedure is always followed. To compare the acidity of two acids, number one, we will always draw the conjugate base. Now, how to draw the conjugate base? As an example, let's write methanol CH3OH. Remove the acidic hydrogen and write the negative charge, so it will be CH3O-. With conjugate base in hand, number two will be to determine which conjugate base is more stable. And finally, the more stable the conjugate base, the more acidic the acid is. First, element effects. Those are the trends in periodic table. Across a row in a periodic table, the acidity of the acid increases from left to right, following the same trend of the electronegativity. As an example, we can compare carbon and fluorine, or their respective acids, CH4 and HF. If you look up the numbers in the pKa chart, we will find that pKa of HF is 3, whereas pKa of methane CH4 is 50. The lower the pKa, the stronger the acid is, and therefore it is obvious that HF is a stronger acid. Now, down the column in periodic table, acidity increases, and this is actually opposite the trend of electronegativity, as electronegativity increases going up the column. We will explain that next. To explain this observation down the column in periodic table, we will look at the corresponding conjugate bases for HF and HBr. The numbers tell us which is a stronger acid. The lower pKa indicates a stronger acid, and that is HBr. But why? From the periodic table, we know that fluorine is smaller than bromine, and in this case, size of the conjugate base actually determines the stability. The same charge of -1 is better distributed on bromine as it is larger and the charge is spread over larger volume. The more stable conjugate base means stronger acid, and this explains the numbers observed. Inductive effect is the pull of electron density through sigma bonds caused by electronegativity differences in atoms. Let's take a look at those two compounds, ethanol and trifluoroethanol. pKa values tell us which is a stronger acid. Now let's explain why. Always compare the conjugate bases. This is the rule we learned previously. Conjugate base of ethanol is CH3CH2O-, and the conjugate base of trifluoroethanol is CF3CH2O-. The difference is obviously here, CH3 versus CF3. CH bonds are non-polar as there is no electronegativity difference between those two atoms. But there is a significant electronegativity difference between carbon and fluorine. Through sigma bonds, negative charge on oxygen in this molecule is delocalized and spread over a larger volume, whereas in ethanol that is not the case. Charge is localized on oxygen. Resonance effect is stabilization of conjugate base through a resonance. To explain this, we will compare ethanol to acetic acid. Again, we will have to write the conjugate base for ethanol, that is CH3CH2O-, and for acetic acid, that is CH3C+O-O-. This is called acetate ion. For acetate ion, we can write another resonance structure if we push electrons from this oxygen towards the carbon and make a double bond here. If we do so, we have to move this pi bond on the other oxygen, and now that oxygen bears a negative charge. Negative charge in this molecule is in this way delocalized over two oxygen atoms and spread over a larger surface. We also learned previously that additional resonance structures bring extra stability to the molecule, and therefore acetic acid is more acidic than the ethanol. The last effect we will learn about is hybridization effect. Comparing the ethane to ethylene and acetylene, their respective pKa values tell us that acetylene is the most acidic, having the lowest pKa number. To explain this, we will look into the conjugate bases. Negative charge is localized on a carbon, but all those carbons are different. In this case, we have sp3 carbon, here it is sp2 carbon, and finally here we have sp carbon. So why is it that sp carbon with negative charge is the most stable form? This has to do with the percent of S character in each of the hybridizations. In sp3 hybridization, there is 25% of S character. In sp2 hybridization, there is 33% of S character, and in spe hybridization, there is 50% of S character. S orbitals are spherical in shape, as we know, and electrons are kept closer to the nucleus that way, so negative charge in sp hybridized carbon is more stable form. Fun fact. In TV show Breaking Bad, Walter White uses one acid to dissolve a human dead body. Now, it is your task to find out which acid that is and if it is even possible to do something like this.